Let's get started. Electrostatic control with ionization. So as an overview, we're going to talk about ionization as part of the ESD control solution. We're going to go through some principles of ionization, the physics of it, the types of ionizers available, or at least some of the types. We're not going to go through all of them, but the types that you'll most likely see in your processes and would you use in your applications, and then go into applications. So I'll show some pictures of ionizers that are installed in tools and things that we're involved with. If you have questions, Tim, if you can keep an eye on the question teams thing, if someone sends a chat question, let me know because I can't see that window.
Sure.
And also just, you can unmute and ask a question anytime. We'll see how that goes. I'll try to stop frequently and ask if there are any questions as well. So solutions to static problems. If you've attended the previous seminars, you've seen that successful static control or ESD control boils down to the application of 4 techniques. Prevention. The best way to prevent an ESD problem is to make sure there's no charged insulators and charged items in your work area next to your ESD sensitive products. That's the most common method. So therefore, if you don't have a required item, binders, coffee cups, pictures of the kids, whatever, that have plastic items that will charge, they need to be off your workstation and out of the work area. That's the best way to prevent it. Some industries allow the use of anti-stats and other chemicals and things like that to reduce charge, but some of the cleaner industries, I'll call them, including medical device and life science, disk drive, semiconductor, don't allow anti-stats, so they're not used as much anymore. But they are still available if in back-end kind of processes. Dissipation, it's a fancy word for grounding. Grounding all of your conductive and static dissipative items is a critical piece of your ESD control program. That includes people, because we're conductive. And then next month, there'll be a packaging seminar, and that's where you'll learn about shielding. So if you can keep a shield around your ESD sensitive product, you can prevent electrostatic fields from getting to it and electrostatic events from happening that affect it. We're going to focus today, though, on neutralization, which is a term that we use for ionization, is the most common way to neutralize the charge on materials. So ionization is part of the electrostatic solution. It's not the solution, not the whole solution, it's just part of it, but it's a critical piece. So if we have an insulated material here, you may have seen in the previous classes that an insulated material can have positive charge or negative charge or both. One piece of plastic or something like that can have islands of charge on both sides, or both polarities. So the goal of an ionizer is to create a whole bunch of negative and positive ions in the air around it, and of course opposites attract. So the positive charge on the insulator will attract the negative ions, and vice versa. The negative charge will attract positive ions and neutralize the charge on the insulator. We provide billions of ions to do this in a typical ionizing environment. If you look at how long a charge will hang around on an insulated material, if you don't provide ionization, this can last a long time. And how long it will last will depend on a lot of factors: the type of plastic material, how insulative it is, what the relative humidity is in the room, the dew point, and how clean that material might be. But with ionization, that's irrelevant. All of those variables, the ionization will take the charge off very quickly. I'm going to show you a video now of how an ionizer will remove the charge.
I'm going to do a short demonstration here to show how ionizers are quite effective at removing charge from an insulative surface. My insulative surface is a piece of Teflon, which of course is something you should never have in an ESD safe work area. To measure the electric field on it, I'm going to use an electrostatic voltmeter, and I'm grounded to make sure I don't influence the measurements. So I'm going to start off by just looking at the Teflon. I haven't done anything with it other than it's kind of sitting near the ionizer, so it's less than about 1,000 volts on it. I'm going to now rub it and charge it up good. And you can see here I'm up to over 20,000 volts. So now I'm going to place it under the ionizer for a few seconds. And here you can see the voltage has dropped already down below 2,000 volts just by a short period of time. And now I'm below 1,000 volts. Teflon doesn't like to let go of charge, so it's going to hang in there, which is one of the reasons we don't recommend having Teflon in your ESD safe work area. But as you can see here, the ionizer is quite effective at removing charge even from a piece of Teflon.
Okay, any questions about that? All right, moving on. There are many types of ionizers. Corona is the most common type of ionizer out there. And within the Corona family, there are a number of other technologies. We're going to talk a little more about these, but AC or alternating current technology is probably the most common, although it's being kind of replaced a little bit by steady state DC. And then another type is what's called pulse DC. And there's variations of the above. The pulse DC are technologies that we use in ionizing bars that are mostly in like semiconductor tools. But the place you'll see that is in some of your processes would be in a room system. And we're doing a lot of garment change rooms and things like that. I'll show that at the end, but that's not for ESD control. That's for ESA control, as Tim mentioned earlier. There's other technologies. There's alpha, which uses a polonium-210 radioactive source to create the alpha particles, which then create ions. And there's also photon ionization, which uses a soft X-ray. Both of those ionizing types are used in kind of, I'll call them hypercritical applications because they're expensive, and they create, automatically a balanced ionizer that's almost instantaneous decay times. And we'll talk about what balance and decay time is in a minute, but those are for very specialized applications, not so much probably in your industry. So Corona ionization, how do we make the ions? What we do with this is we get a sharp point, we put a high positive charge on it, and that is used to create the positive ions. It modifies the outer shells of the electron or the atoms by ripping an electron off and leaving the atom charged or molecule charged positively. Likewise, the negative ions are made with a sharp point with a high negative voltage on it. In this case, again, an electron gets stripped off or knocked off, put onto another atom or molecule, which creates different polarity, a negatively charged molecule. Those are our physics lessons for the day. The AC technology. And the AC technology uses one emitter point, and it is connected to both the positive and negative sides. It's using the AC signal from your line voltage to change the polarity of the emitter point. And when it does that, it's doing it at 50 or 60 hertz, depending on what part of the world you're in, what your line voltage is. This is probably the most common ionizer that you'll see in your processes at this point, because they're hardcore. They work great, ionizers, and you can tolerate blowers. So one of the advantage of this ionizer, of course, is that you get a lot of very high ion output of both polarities. They also maintain a pretty good balance. The downsides of these are that because you're using the same emitter point to create both positive and negative ions very quickly back and forth, if you don't get those ions moving away from the emitter point, they recombine very quickly, and you'll end up with neutral atoms again, neutral molecules. So almost all of these technologies utilize a blower type operation. You can see that we have overhead blowers and benchtop blowers, and I'll talk a little more about that. But because you're using the same emitter for both polarities all the time, 100% duty cycle, basically, you got to deal with more frequent emitter point maintenance. We'll talk more about that as well in a minute. Steady state DC is the other very, very common ionizer technology. And again, similar situation. Here we're using but two separate emitter points. One creates positive, one is attached to the positive power supply, the other one's attached to the negative power supply. And they they both create the ions at the same time. But again, you're creating both positive and negative ions in the close proximity. And if you don't do something with those quickly, i.e. with a blower or airflow through a hose or something, they will recombine very quickly. So they require high airflow as well. This is probably not accurate, really. Most steady-state DC products, good steady-state DC products, have plus or minus 3 or 4 volt balance now. Again, 100% duty cycle. You got to deal with making sure your emitter points are working properly. We're going to talk a little bit about the ionizing air guns and inline ionizers here. The inline ionizers have the emitters within the box here, and you're blowing nitrogen or air through this, and you can direct that airflow right where you need it. These work great within tools and applications like that where you need a lot of ionization in a very, very close proximity. You put that tube right where you want it. And of course, blow-off guns, what you've seen probably in your process. There's 2 types that we manufacture and provide. One is the Top Gun 3, which I see in a lot of your processes. And here it is in use in a diagram. The other one that's popular is the Air Force. Both of them offer filtered air. They have a filter built into them. The Air Force gun has replaceable emitter points. I believe the Top Gun does as well. It's a little harder to replace, but it's there. It's an option. The Top Gun has a foot plate and also a sensor that it'll detects an item's below it, and it'll automatically turn itself on. So there's good and bad features of both of those. So those are our blow-off products. Again, are there any questions at this point? So
yes, I do have a question.
Okay.
Those require nitrogen, you mentioned?
Nitrogen or CDA.
Okay.
You just want a clean air source on. Did you talk in the blow-off guns?
Yes.
Yeah, those are most people use just CDA with them and use a good filtered CDA source.
Okay.
Okay.
Thank you.
Carl, excuse me. This is Tim. I have one more question.
Mm-hmm.
This is a write-in. The question is, which technology is more effective for plastic type and fiber type? Example, Tyvek insulators.
Either technology works. The differences in the technology are even though we manufacture the ions differently, you're just making an air ion. Now what you want to do is you want to get that ion to the location as quickly as possible before it has a chance to recombine. So there really isn't a better technology for a particular type of charged insulator. Either one will work. Good question. Anything else? Okay. So we're going to talk real briefly about how do we qualify and do what we call compliance verification testing on ionizers. So the qualification testing utilizes the standard. It's labeled ANSI ESD STM 3.1. This is one of the ESD Association test methods that Tim and I actually probably worked on together a long time ago. It specifies that you do what's called a decay time and an offset or balance test. I'll show you what those are in a minute. The testing is performed in a specific pattern that depends on the type of ionizer. Is it a workstation versus benchtop versus a room system? But the standard has various test methods for all of those different types of ionizers. Then you have compliance verification testing. There are some specific test methods for that from the ESD Association. This test it's a quick test basically that you do after the ionizer has been installed and is being operated in your workstation. You want to make sure that it's doing what you intended it to do. Just like we test wrist straps, or we use a monitor for the wrist straps, and we test grounding on a regular basis to make sure that something didn't break. We want to do that with an ionizer as well. Again, the difference being that qualification testing is something that, say, Tim will do, or he'll evaluate a laboratory's test done with this to pick this ionizer vendor over this ionizer vendor, or this particular ionizer type over this one, and he puts them on an AVL. You buy them, put them in your work areas, but you want to be able to do this compliance verification testing to make sure that they're working properly after you've installed them and on an ongoing basis. So those are the different types of tests you'll hear about. The qualification test is typically done with what we call a charge plate monitor, or a CPM. This is the one we manufacture. It does both ionizer balance and also discharge performance. The discharge test is done from 1,000 volts to 100 volts, both positive and negative polarity. Very, very detailed specification description in this document if you're interested. Tim has done some research and has approved this handheld unit for compliance verification testing. It does both the balance and the decay test as well. If you are going to have a lot of ionizers in your process, give Tim a call and get one of these ordered. You're going to need it. Here's a video on how you use a CPM to do both the balance and the decay test.
Hello. Today I'm going to demonstrate how to use a charge plate monitor to do a simple measurement to evaluate the performance of a benchtop blower. Here we have our benchtop blower, and the airflow is coming out of it and hitting the charge plate monitor perpendicular. This 6x6 inch plate is the charge plate monitor. The larger plate in the back is a ground plane, which I have grounded to the back of the electronics unit. The electronics unit is also grounded to AC ground. In addition, so that I don't impact the measurements, I'm going to wear a wrist strap as well to make sure I'm grounded. The ionizer is operating. It's in whisper mode, but there are plenty of ions coming out of it. So I'm going to start this test by going with a balance or offset test. The balance test basically measures how many volts the ionizer is putting on the plate. And you can see in this case, the ionizer is putting up negative 9 volts on the plate, maybe negative 10. Kind of bounces around a little bit. Normally you run this test for 30 seconds. I'm going to not run it that long. So now we'll back out to the main menu and we'll do the other tests, which are a positive decay test and a negative decay test. So the positive decay test, the charge plate grounds itself, and then it charges itself to 1,000 volts positive and measures how long it takes the ionizer to decay the charge down to 100 volts. In this case, it took 1.6 seconds. Let's stop that measurement. Go back to the main menu and do a negative decay test. And here you'll see the charge plate will go to a negative 1,000 volts, a little bit more than that, and then how long it takes down to a negative 100 volts. And you'll see that this case, it took a little bit longer, and that's because the ionizer is putting out more negative ions than positive ions, and therefore it takes longer to do the negative decay test. This is one of the reasons you want to have a balanced ionizer as close to zero as possible. But that's how you evaluate an ionizer using a charge plate monitor.
Okay, any questions about that? Relatively straightforward.
I do have a question, but it's more
Okay.
following the question somebody made on through the chat. Let's say I have a machine where I process trays that are covered with Tyvek material, and I spray that, and that machine is about, say, 2.5 to 3 meters long, right? And that tray is placed in an infit gate, and it goes across the machine, and it spends maybe 2.5 minutes, because it has some stations where some processes take place.
Mm-hmm.
If I spray that tray at the infit gate, how much or how long will the ionization be effective?
Well, the ionization is basically, it'll take the charge off.
Yeah, I know.
If you're under it long enough. And as long as you don't touch that material again, it normally won't recharge. There has to be some form of charging mechanism on that material to charge it back up. So if you don't touch it, it likely won't recharge. But as soon as you touch it again, if you don't have ions present when you touch it again, it will recharge. So you'll need to, as long as you continue to touch, and then you touch it or the machine touches it, a lot of times these Tyvek sheets, when they're getting placed on the trays, they go through a variety of rollers.
Yes.
And I've had people want to ionize the beginning of that. And I'm going, yeah, but as soon as it goes around that roller, it's going to recharge. So you got to add more ionization.
Okay, so that's
ideally you want to ionize it right before you put it, on your product.
Yeah. Okay. So you advise that I may put some points, ionization points across the machine.
Correct. Yeah, you need them in various locations in most situations. If you have a specific application, we can help you with that. We do that regularly. We'll look at the tool and figure out where we're getting charging occurring and where the best place and the best technology of ionizers to put in that operation.
Because we have an issue here in Dorado. The trays. We know that the machine is producing some particles, had some particles inside, and more often than not, they end up in the tray, right?
Sure.
Over the Tyvek or at close to the tray, adhere to the tray, and it becomes a problem.
Absolutely. Yep. That's more of a conversation for the ESA discussion because that's what you're fighting there. But the good news is that if we resolve the charge on the materials for ESA, it works for ESD as well, and vice versa. So it's a charged material issue, and if we can resolve that, it'll solve both problems. But your specific questions about ESA, and there's some other things we do, like ionizing the garment room and things like that. We'll talk more about that towards the end of this talk. I'm going to do a little selling for the ESA presentation, and we can definitely recommend you join that call because you'll learn a lot there about various techniques we use to resolve that kind of a problem. Good questions. Thanks.
Okay, thanks.
Hi, this is Tim again. Richard, I have started to work with Dorado here a couple of weeks ago. I met with a team member last week, and we looked at some of your quality data coming out of your final pack area. So we are starting to engage. I have discussed preliminarily this topic with Carl here, our presenter. And I've also sent down some Microsoft glasses or Microsoft HoloLens to one of your team members so we can do some remote Teams meetings and fix your problem in Final Pack. So I've got your name down here. I'll make sure that you're copied on our actions as we go forward with Dorado. Okay.
Thank you.
Thank you, Carl.
You bet. So here's we're going to talk a lot about overhead versus benchtop blowers. I wanted to show the difference here. The overhead, of course, hangs up above your bench and blows down. The benchtop is more focused, and you blow it on a specific process step. The benchtop also can be. We have smaller versions of those, and I'll show you pictures of those that can go inside tools. Similar to what you were talking about with your trays. They're typically used a lot of times on a like a test handler. I'll show you pictures of those in a minute. So when we're doing this qualification testing, this is the kind of differences, different test methods that are done. So here's a benchtop blower diagram showing the green is your tabletop, and we're looking from the side. So we'll place the ionizer at specific locations in front of that blower, but not only just directly in front of it, but also off to the sides. And you can see that some ionizers will have a very narrow cone of air. Some will have a very wide cone of air, and the decay times and performance at these different test locations will be different. And we want to be able to understand that. We actually sell some ionizers that have what we call a collimator on the front. And so in that case, test point 2 through 8 looks really good, and 1 through 10 and 3 through 12 are horrible. But that's by design. We either go inside of a tool, and we're trying to focus that airflow where we want it to go. The overhead blower has a similar test pattern. Again, here's the table from the side view. The overhead ionizer is hanging above it and the airflow is coming down. We'll place the charge plate at 4 locations across, but again, we do not just right under the ionizer, but also on either side. So we're going to actually cover the entire workbench. Here's a video showing the differences between the two ionizers. Now, in this case, I'm not using a charge plate monitor because everyone should have to wait and watch the decay times, you know, over and over again. I use what's called an air ion counter. Talk a little bit about it here. What it is, it's basically measuring the density of the ions in the air at various locations.
Hello, today we're going to evaluate the coverage area of a benchtop ionizing blower. And to do that, I'm going to use an air ion counter. An air ion counter is basically measuring the density of the ions in the air produced by the ionizer. And this meter maximizes at 200 million ions per cubic centimeter. And you can see that when I'm right in front of the ionizer, that's what happens. It pegs the meter. You'll see, though, that as I move further away, the ionization quickly starts fading away. The ions are being recombined, and we're not getting coverage to clear to the end of this workbench. You can see it drops down fairly low, fairly quickly. And the other thing I want to demonstrate, again, if I'm right in front of the ionizer, I get 200 million. But if I move just a little ways out of the path of that airflow, the ionization quickly drops off. If I do the same to the back of the bench, same thing happens. The ionization drops off pretty quickly, basically to ambient levels. So a benchtop blower works very effectively when you're focusing the airflow where you need it. But if you need a full bench coverage, the benchtop blower may not be the best choice for you. Here we are again. This time I have a 3-fan overhead blower hanging up over the workbench. I have the blower balanced, pretty close to 0 volts on all 3 fans. And I'm going to show how the coverage is affected with this blower to kind of compare it to what was going on with the benchtop blower we showed earlier. So I'm going to use my air ion counter again. And as you can see, when I'm centered underneath the fans, I maximize the meter well over 200 million ions per cubic centimeter. I'm only looking at the positive ions because, again, it's a balanced blower, so shouldn't be any different. And even as I move towards the front of the bench, I still have a maximum number. It drops as I go in between the fans, but then it goes right back to pretty much maximizing it. The only place we have weak spots, I don't know if you can see this on camera, is when we get over in the corners of the benches. The numbers drop pretty good. But as soon as you move, again, kind of underneath the fan itself, they go much higher. In the back of the bench, again, I get over 200 million ions per cubic centimeter. So if you need to cover an entire workbench, an overhead blower is a much better option for you than a benchtop blower would be.
Okay. Now there's, I'll let me talk about this, then we'll ask questions about the video. So I took some of our data sheets and I looked at the differences in decay times using the different benchtop versus overhead. And you can see benchtop blower performs really, really well with decay times in 1 to 2 second range. Right in front of it, 2 to 5, 5 to 10, and then it gets kind of longer out here. Now you can change that by how fast you run that blower. If you run a faster blower, you'll get better decay times out here. But you can see that on the sides, as you saw in the video, the decay times are quite excessive. I'm trying to equate decay times to ion density. As long as you got some ions on that air ion density counter, you're doing pretty good. You get some reasonable decay times. But when you get to ambient, of course, then you get very long decay times. The overhead blower, the corners aren't very good a lot of times, but of course you cover the bench much better. This is about a 5 foot by 3 foot bench, so That's what we're trying to measure here. So going back to the video, are there any questions you have about how an ionizer performs differently, benchtop versus overhead? Okay, move on then. So here's a picture of an overhead blower in use. This is a disk drive manufacturing facility. This could be any manufacturing facility where you've got rows of benches, and you can see that we've populated this entire clean room with 3-fan overhead blowers. You can look at this workbench and realize how disastrous it might be trying to use benchtop blowers. They're going to get blocked by other items. You're going to get knocked over. Here they can just run and people kind of ignore them. We can play with the heights and the fan speeds of these also, depending on, this is a sitting operation. We have a lot of places where we install these overstanding operations as well. We typically have to move those a little higher, which of course makes your decay times longer, but we can kind of offset that a little bit by fan speeds if we need to. There's a whole engineering process to understanding how close you can put the ionizer and how far away it can be versus fan speeds versus how fast things are operating. You know, if you've got a very slow operation, the items are sitting there longer underneath the ionized airstream, so you can tolerate a longer decay time. Versus, you can imagine a pick and place machine where parts are moving very, very fast. You may need a decay time that's much, much faster. Emitter point maintenance. One of the key problems with corona ionization is that it tends to condense what we call airborne molecular contaminants. Here's a picture that actually Tim provided. He found this at a supplier of yours, and this ionizer was not performing. The decay times were excessively long, if they were occurring at all. The balance may have been off as well, I don't know. But once he cleaned these emitter points, the ionizer popped right back in and was working fine. This particular ionizer has, as do many of our ionizers, have a little brush knob on the front. So cleaning the emitter points is very, very easy to do. You just spin them, and there's a spring that pulls it back. So you just clean the little brush runs around and cleans those emitter points off. These little fuzz balls come from, again, the condensation of airborne molecular contaminants. They need to be cleaned off regularly. The longer they're on there, the harder they are to get off. So we tend to recommend that we have some automated systems now on some of our latest technology blowers that have an automatic point cleaner, and the default setting on those is every 7 days. So if you could talk your operators into running these things across once a week, I recommend them. That's part of your workstation setup. You know, the other thing to be aware of is that when you knock this off, you're going to create particles. So you don't want critical product underneath it. But you're going to clean your workstation anyway when you start your shift. Go run through, run around, clean the emitter points real quick. It takes 5 seconds, if that. Then clean your workstation and then go to work. That would solve a lot of problems with ionizers having problems. The longer you leave this on, the harder it's going to get off. And at some point, you're going to need to use a swab with IPA and really work to get that emitter point clean if you don't do this on a regular basis. Any questions about emitter point maintenance?
Yes, Carl, this is Tim. There was a write-in question.
Okay.
The question is, what types of molecules generally comprise AMCs? I'm not. Do you know what AMC is?
Oh, yeah, AMC is
sorry, it's an acronym.
Airborne molecular contaminants. Typically, they're organometallics. They're a number of variety of things. And if you're asking what the composition of this white fuzz is, I couldn't tell you. I believe there's been some research done on it, and that's where they found out that indeed it's coming from the air. It's condensation of the air, contaminants in the air. So basically, I believe it's a lot of just the organics and things that are floating around in the air that are causing that. I'll have to check that out, and I'll get that answer back to Tim. I'll see if I can find out, and he can get that sent out. Good question.
That's great. Thank you.
That's a tough question.
Thank you. Bring on those tough questions for Carl.
Yeah,
He can handle it. Next question, actually coming from Clonmel, Ireland. The question is, at what range are these effective?
Ionizers? It all depends on how much airflow you can tolerate. The overhead blowers, let's call those are the most common ones. Generally within 3 to 4 feet, depending on which ionizer. We have some of our products have what we call a whisper mode. I mentioned that in the video. We can barely hear the fan running. Those tend to work the best, probably at 1 to 2 feet. You get further than that, and the airflow is just not there anymore. But the FPD blowers, which are our highest volume blowers, they put out, and also these new technologies have 4 fan speeds. So the whisper mode, and then all the way up to, we joke that if you turn this thing face down, the benchtop blower, it would blow itself off the workbench. A lot of airflow, they're kind of noisy. Those you could probably operate 4 feet away, and you get pretty good ionization 3 to 4 feet away. So that gives you the range, probably between 1 and 4 or 5 feet, depending on the ionizer. Good question. So here's some examples of ionizers in use. So on the upper left-hand corner, you can see the box ionizer up here blowing down on the tray of parts. Another one down at the bottom in a test handler. Again, the ionizer is blowing down on these trays, ionizing the parts before the machine comes, or the operator or the robot comes and picks them up. The other option is the ionizer. The robot may put parts in these trays, and again, when the robot gets done touching the part, it's going to charge it. So that's a good time to ionize it as well. Here's a compressed gas ionizer, an inline ionizer with a manifold. So this tube here has holes drilled in it, and we're blowing air into here, ionizing it, and it's being pumped out. And you got to deal with pressure differentials and things like that for decay times. You're going to get better decay times here than you will over here at the end, but that's an aside. Here we're using this to blow ionized air down on parts that are moving on a little conveyor. Here's another test handler photo with an ionizer. So here's your ionizer. Here's the robot that's, oops, what happened here? Picking up various parts in the trays below. Again, these are situations where we want to ionize the part before and after it's touched as much as possible, and get the decay time off the charge off as quick as we can. So we want really fast decay times in these situations. So we're going to talk. Oh, go ahead.
Excuse me, Carl. We have another write-in question.
Okay.
Sorry for interrupting. The question is, with a overhead ionizer, where do the particles go?
They go where the air blows.
Right.
Just like the ions do. With ionization and particle control, it's all about airflow.
To give you some context, excuse me again for interrupting, I think William Gonzalez here is calling in from Dorado, and I believe, if I remember, he's a quality engineer in our final pack area. Is that right, William? I believe so. So he's asking, I think we have a lot of folks calling in from Dorado, because I think we have a significant ESA problem. Not that we don't have a significant ESA problem across the network, where some of you have ESD programs and some of you don't. You all have particle contamination problems that a good ESA program will help mitigate, which is why ESA is strongly on my brain, and that's why we're coming up with an ESA session in June, July timeframe. Okay, sorry, go ahead, Carl.
Okay, good. Well, that's right. Good intro to this, where we're going right now, because I'm kind of transitioning now into a sales pitch for the ESA discussions later. We have the overhead blowers blowing down on a workbench, and then we have I mentioned room systems earlier, and this is the emitter point that you'll see. So out of one side is positive, and I may have that mixed. I think this one's positive and this one's negative. Doesn't really matter. except there is a red stripe around the negative one, I believe. And what this does is it cycles on and off, positive and then negative, and then there's some off times. And we do that. We program them to take advantage of either a lot of airflow or very little airflow from the clean room. But you can see that we're going to ionize the entire room with this kind of ionizer. Whereas in this overhead blower, we're just ionizing the workbench. And where we'll use that is in controlling charge and controlling particulates. So here's what you're up against. In life science manufacturing, ESA contamination is the leading cause of yield loss and customer complaints. And what we have found is that if we can mitigate the charge on the materials and on the particles that are floating around in the air, more on that later, that's part of the ESA tutorial, you can, this is the difference you have in your product. So consider this your Tyvek cover or a catheter in this case with charge on it. You're going to get, and you can easily charge it to 12 to 20,000 to 50,000 volts. It is pulling particles from as far away as a meter away in your room. And yes, your floor is that close. So, and this is in an ISO, these are both done in an ISO 8 process. The only difference is that this item was charged to 12,000 volts, which is, again, is very easy to do. And this item had no charge on it. So one of the other options or operations, I mentioned garment change rooms. We'll ionize the garment change room. While these garments are hanging underneath the ionizer, they're kind of, to some effect, being cleaned. You got clean air coming down, you got ionization, knocking the particles, discharging the particles, and then they can just fall to the floor. We know this works because when a customer installs the system and turns it on, we get a call complaining about the fact that they got to clean their floor 3 or 4 times more often than they did before. All the particles are going on the floor instead of being carried into the clean room process. We also augment that with some ionizing blowers. These are the FPD blowers I mentioned that have a lot of airflow coming out of them. So we can hang those above a door, and we put them in the entrance to the change room to start the process, and then kind of finish it off towards the end. And here's our little guy. He's got particles attached to him, and here they're being discharged with the ionizer. So that's our sales pitch for the upcoming ESA training series. So stay tuned.